what I'm going to talk about today will be mostly quite conceptual things. So brace yourself, it's not going to be specific Hamiltonians, it's just really conceptual stuff. In particular, something I find very important and very interesting, maybe some connections between the notion of quantum Markovianity, multi-time correlations, and many-body quantum systems. And to discuss those notions and to understand the core part of this talk, I will first introduce a framework that I like to use a lot, and namely the process tensor framework. It will be very helpful in understanding those relations. And this all together will then quite naturally lead to some numerical method to then use for many-body open quantum systems, which I will be talking about towards the end of the talk. So let's start with the process tensor framework to understand open quantum systems in general. So the way I see it, the process tensor framework is a sort of multi-time generalization of the dynamical map. Okay, so the dynamical map is the thing that people usually talk about when they talk about open quantum systems, but the process tensor framework is sort of more general and more capable in that sense than the dynamical map, and we will talk about how and why. So let's first understand the dynamical map a little bit, and for this I will draw a lot of these diagrams, like quantum circuits, which you're also free to interpret as tensor networks, right? One thing I want to mention right away is that everything I draw will be in Liouville space. So we'll always talk of states as density matrices, and all the matrices that evolve something are actually superoperated. Just everything gets very simple from this language. So the problem with an open quantum system, you very often formulate like you have a system and you have some environment. Here I have lots of lines here for the environment, which is supposed to represent it can be anything. It can be a small system, large system, it can be a continuous degree of freedom. And the dynamical map is something where you have a unitary transformation on this entire system and environment, and then you measure the system at some later point in time. And you don't just have this for one time, but you also have this for the later time and for even later times. So this is the dynamical map, and most of the literature of open quantum systems concerns this quantity. But in fact, this is not all you can measure in an open quantum system. You can have multiple interventions multiple times. And this is going to be important. So let's think about what are the most general things you can do to an open quantum system. And then we can start with the initial state. So initial state might not necessarily be a product state, it might be just an entangled state. And this is usually the more natural thing, because if you start your experiment, typically they will be in some steady state of the entire system and environment. So this will be normally in an entangled state, which I draw here like that. So you see the sort of tensor network idea behind this as well. And then what can you do? You can measure something and reset it. You can measure it, forget about the outcome, and reset the system. Can perform a unitary transformation in the system, or unitary in the system and some ancillas. Or in fact, the most general thing you can do with just access to the system can be described with a completely positive map on the system and some ancillas. The environment, per definition, in the way we're talking about it here, you do not have direct access to. You only have access to the system. So after you've done that, there will be time flowing. So here I'm thinking of this happening very fast. There will be time flowing, and then you can do it again. And then will be some evolution, and do it again and again and again. So this here is the most general thing you can do to an open quantum system if you think about time being somewhat discretized here. And the process tensor is this part of the circuit. Okay. And now you might say, well, this is not very helpful. This is just the entire system environment dynamics. But so why am I thinking about this? And the important thing here is something that's very natural if you think about it in terms of tensors, is that for this tensor here, it's only really the outer legs that matter. So if you reinterpret this as a tensor network, you see that these parts here are sort of the internal legs of something that's in the matrix product operator form here. Okay, so they don't really matter directly to the process tensor here, but they're sort of the internal degrees of freedom, which I actually don't care about. So you can think about it, although in practice you don't quite do it this way. You can think about it that you could numerically use this by just truncating this space in between them, and then have something that, for example, a process tensor in a specific form, like you can create tensors in different forms, in this case, in a matrix product operator kind of form. Okay, so this is really, let me summarize a few things about the process tensor. So the process tensor does not only code the dynamics, it also encodes the multi-time correlations of the system. It's going to be important. But in principle, as you've seen, there are many legs. It scales exponentially with the number of time steps that you're considering. This is like the path integral. So it is one way, it's another name almost for it. But it can often be represented efficiently as an MPO. Right? And this is where numerically usefulness comes in. Okay, so numerical usefulness, I'll just give you an overview here. I'm not going to explain those methods here really, but just tell you that they exist and that they can be, this concept of the process tensor can also be leveraged numerically and not just conceptually. So the most straightforward thing you can do is constructing a process tensor in this MPO form by just starting with the tensor network of the full system and environment, and then contracting it in an order such as that you have only the system left over with some open legs towards the system, and you've sort of traced the environment but kept all the legs in time. So there is a bunch of publications doing that. They don't call it the process tensor, they call it the influence functional, they call it quantum comp. There's lots of different words, but these are mathematically the same object. So, but essentially you don't need to do this full simulation. You can also more directly construct something like a tensor network for such a process tensor. For example, for bosonic Gaussian environments, so this sort of tempo that Peter talked this morning can be formulated to give you something like this process tensor. But there's also fermionic versions of that. I think that was a question, and many others. So this is not a complete list. There's also another method that we will hear later on by Eric Gauger, I think tomorrow. Another method called ACE, where your environment might consist of some discrete set of environment modes, and you can construct a process tensor. And also, in principle, I want to mention this, you can measure it. And you can measure it by just performing measurements on the system. You don't need to measure anything about the environment. Okay. Yes, please.
Are you using the term tensor in a very general way? Could it be something that is not a tensor?
This is a tensor. This must be a tensor. So the thing that I showed is a multilinear map. So it is a tensor. It's proven.
What about this map by algorithm? You can think of it the same way.
That is a good question. So there might be different representations.
Which algorithm?
This small matrix path.
Yeah. So this is a very good question. So this part of the tensor network that I showed you is very clearly a tensor. So that's very straightforward to prove that, and it has certain certain properties. And even if you have some other representation, so here I have the process tensor in a matrix product operator form, but you can have other forms. And I'm pretty sure that this small matrix representation you're talking about, which I need to yet understand better, at the end will also be a representation of a process tensor, but not in
it is, but it's more beneficial to look at it as in terms of the small matrices, right? So I mean, I could go back.
So you see here we have this is lots of different things. I mean, maybe it's more efficient, but I'm not talking about efficiency here. I'm talking about the concept. Okay, and here this is a whole range of different environments, and it doesn't matter where it comes from. And this is exactly the point I wanted to make here. This point doesn't matter where you get this this process tensor from. Once you have it, you can forget about with what method you made it or what it actually physically represents. This will tell you how a system will evolve with that environment. Okay, and then you can use this regardless of where it's from in many different ways. You can look at optimal control. So Paul will talk about this on Friday. You can use it to perform optimal control procedures on non-Markovian open quantum systems. You can learn something about dynamics of the environment, which also Peter was talking about. You can combine it with multiple environments, you can perform mean field things, and you can look at dynamics of change of open quantum systems. Okay, so let me pause here for a minute and see if there is any. So this sort of concludes the very brief introduction to process tensors. But let me see if there's something that needs to be clarified about the process tensors. Yes.
Good question. When you say continuous, it's for the bars, an infinite number of sides in the bar. But all the times are always discretized in every method. Is that correct?
Yes.
Yes.
Yes. Exactly. Okay. Anything else?
So I have a question.
Yeah.
Are you proposing to, to construct the whole evolution of this object for later on using it through an ancilla, or in what sense, constructing all this first is a strategy for solving specific tests?
So constructing this all first is a strategy that's used extensively on all the methods that I show here. So for example, for this optimal control, the idea is that you have all the complexity from a non-Markovian environment, right? And you can put this all into the process tensor, and then you've done basically the heavy lifting of the whole problem. Once you have that, you can try out many different system Hamiltonians, many different system Hamiltonians that and then optimize your procedure towards it, and you don't need to redo an entire calculation. So, and also here, you've already truncated the non-important correlations between the system and environment, and you can more focus on the correlations between the systems. And so this is beneficial numerically in a lot of scenarios. Yeah.
Can I
just press once?
Just press it. Press and hold.
Oh, you have to hold it.
Oh.
Yeah.
Can I define it as a map in a more general way?
Yes, it is a map, and it's a multilinear map, therefore it's a tensor. Yes.
But its representation could be not something
Could
a
be
smaller
anything.
object than a tensor.
No, a tensor is a multilinear map. Right? That's the definition
Yes,
of a
but
tensor.
I-
How you
I
represent
can-
it doesn't need to be a full thing.
Yes, I can store it in different ways that does not
Yes.
require the full tensor
Yes.
storage.
Sure.
So,
Yeah.
I think the distinction may be that it's multi-time versus two-time.
Yes.
So from your talk earlier, I understood that the small matrix pattern integral it gives you two-time correlations.
But there are many of them, so in the end, when
That's
you
right.
combine
But-
them,
but
you get
this-
multiple.
I don't think so, but we can talk about that.
I mean, that's it, because it's entirely equivalent to the, it's entirely equivalent to the quapi tensors. That's where it came from. But it's a more efficient representation because it does not require a tensor.
So I'm not just talking here about continuous. This is very general. This is true for any environment. So okay. So the way I see it, this is a process tensor, and there are many different, or an influence function, however you want to call it. There are many different representations, and I'm sure there are more efficient representations or less efficient representations, but they're the representation of the very same object. And this is the object I'm talking about. Yes.
So just to clarify your point, I think if you have the kernel of the Nakajima's Danzig equation, that's not a process tensor.
Exactly.
Why not? It does the same job. Okay, it's not a tensor, but it does the same job.
Because
Okay.
this does more jobs
Okay,
than
I
like
will,
the
I
kernel
will, I
of
will
the
talk
Nakajima's
about
Danzig
I will talk
equation.
about all the jobs that it does. Yes, exactly. I will talk about all the jobs that the process tensor in general can do. And so why do we want this? Why do we need this description? So all the methods that I showed you just before, generally go under the name of non-Markovian, so numerical methods for non-Markovian open quantum systems. And you might think that for something that's, for example, Markovian, in the sense that its evolution is governed by an input master equation, you do not need such a description. But if you're interested in multi-time correlations of some system, in fact, it turns out that you do. Or in other words, non-Markovian effects do play a role in multi-time correlations of systems, even if the system can be described with a Lindblad master equation. Okay, so that might be shocking. So, but I will give some examples. So, talking about the Lindblad master equation was one way to think about Markovianity, or many people use that. But actually, in the quantum information community, people usually consider something called completely positive divisibility, which is slightly more general, but essentially the same thing. And something is completely positive divisible if you have an evolution which can be separated into small chunks of completely positive maps. And this is something, if you have something that's a Lindblad master equation, if the evolution of your system is described by a Lindblad master equation, it does imply that the evolution process is completely positive divisible. And essentially that means that if you have your system and environment, you can replace this with just the evolution of the system with this map, the Lindblad type of map. But it does not mean that you can do the same if you're considering multi-time correlations. Okay, so something where you have multiple interactions of your system with your environment might actually be different than what you get, even if the process is completely positive. Or in other words, even if something is completely positive, and this does not imply that the process tensor factorizes in time. Okay, at this point, this might all be quite technical, and there is some very nice work on exactly that here from Miltz, and also Kevin is there in this list. And there are many examples, but I made up an example just quite recently that also stresses this point, and I hope will help you understand this statement here and also its physical relevance. So the example that I'm thinking about is something that is a process that can be described with a Lindblad master equation, but has non-trivial multi-time correlations. So think of the following. Think of the defacing process. You just have sigma x defacing, sigma y defacing, sigma z defacing. And now let's think of a stochastic mixture of this. So you have some system that has this defacing, but it has, you know, either one of those three. And there is some probability x1, x2, x3, which it has defacing in x, y, or z. And it turns out that such a process can be described by a Lindblad master equation for a specific set of probabilities. So for example, if they were all equally likely, that would be here just in the middle. This is something that you can write down a Lindblad master equation with positive decay rates. So you think it's all fine. Okay. And now, if you have, if I take exactly that, and the following argument is not fine-tuned to having exactly this 1/3 in each of the decay processes, it's actually true for the entire surface that I showed you. And you consider the following. You have an initial state, rho 0, which is just linear combination of x and y, and you let this evolve and then measure along the y minus x axis. Okay. Then you reinitiate the state and you evolve it again. So the Lindblad master equation that follows from what I showed you before will tell you that this state will just directly decay towards the center of the blocks here. Okay, so it will give you always an equal probability with plus and minus of this n. And it will do so the first time, and it will do so the second time. And they will be completely uncorrelated. Okay, but let's think about what actually physically happens. Physically happens is you have three equally likely cases where you have a sigma z dissipation, a sigma x dissipation, and sigma y dissipation. But if you have this sigma y dissipation, you will have it for both of those instances. So that means that the measurement outcome of the second will be correlated with the first. Okay. So although you have a completely positive divisible map here, in particular a Lindblad evolution, the two-time correlations are not given by that Lindblad master equation. Okay? They're actually given by a process tensor of a bond dimension of 3. It's very easy because this bond dimension 3 is exactly in which of those three cases you are. Okay, so you just have here a small bond dimension with exactly those weights of this x1, x2, x3. Okay. So this shows how important these multi-time correlations can be.
But if you done this by solving the exact dynamics, you would have captured this.
Exact dynamics of what? The exact dynamics
If you
of
have
the,
Hamiltonian and
of
solve
the
the
entire thing, yes.
Yes. Yes.
But I don't
the
know.
entire
Yeah,
thing.
that's true. But you don't do that. Usually people are happy to say like, oh, I have an evolution and that looks like a Lindblad master equation.
But that's wrong. We know that.
Good. And now everybody knows it. Okay. So another thing, another quick example. I don't know during this time. Okay, I have a little time now. This was just a correlation. In fact, you can also construct examples where you have signaling. So you have a completely positive, or you have a Lindblad type master equation. But in fact, if Alice prepares something completely forgets about what happened, can Eve recover something from what Alice prepared? Generally, yes, but even for things that can be described with a completely positive divisible map, this can be true. It's a complicated example, which I will not explain here, but essentially here, you can encode this information, in this case, in a 4-time correlation. So you have no information in the single time in the evolution of the thing, but you have all the information in the many-body, in the 4-time correlation. Okay, so this establishes hopefully that multi-time correlations are important, and many different places where this shows up. where they're also important is in many-body systems. And this is maybe all obvious, but I think it's important to appreciate. If you have a system interacting with some environment, so here I have a system, Hamiltonian part, environment, and interaction part, you can look at the entire evolution of the system and environment, and you can usually, if you have a small enough system, small enough time steps, you can trotterize the entire evolution. And if your system now also interacts with some other systems, you have essentially the same picture. Okay? And here what you see is that this environment interaction part here is the very same, but from the same argument, you see that this other system parts essentially probe multi-time correlations of this first system. Okay, so even if you could describe this with a Lindblad master equation, you wouldn't be able to describe this with the same Lindblad master equation. And this is also in a way well known as sort of the local and the global master equation. But you see now hopefully how those things are actually connected. So now if you want to actually describe this, you can either have like a new Lindblad master equation, or you just do the most direct thing and properly describe those multi-time correlations. And this is exactly what you do with the process tensor. So here I transition now to the numerical method, hopefully quite smoothly, because if I want to solve this numerically, I can just compute this process tensor and put it in some matrix product operator form, depending, of course, what my environment is. So it's this whole list of it. And the most convenient for this purpose is to consider it in the matrix product operator form, although there might be different representations. And you can very nicely also combine this with other methods for this many-body system. For example, here you can just use time-evolving block decimation to solve this. Okay? And you can even have a scenario where we have every system connecting to its own environment, and this is also very similar to the idea of this modular path integral, as you have. The difference is a little bit in the concept that I do not care where this process tensor here is coming from. Okay, so this can be something from Ionic. This can be something I don't even need to know how it has been computed. Once I have it, I can evolve this many-body open quantum system. Okay, so here I'm just showing. I don't know how I'm doing this time, but just maybe 5 minutes. I just showed that one can actually.
Minutes if you need us some time for questions. So.
Okay, so I can relax. And so here I just show you some physical examples of where we actually use this numerical method that follows from this. And what we can do, for example, is we can consider an XYZ Heisenberg spin chain in the sense that it has an anisotropy, meaning that you will not stay in a sort of a single excitation subspace, but it might actually go to more excitations. And you can couple some strongly coupled bosonic environment to each site. And using this sort of approach from before, you can first use something like time evolving matrix product operator method to compute the environment part for a matrix product operator process tensor, and then combine it with the TEBD to solve for the evolution of this whole thing. And here I'm looking at the spread of a single excitation that starts in the middle. And we can see that there's some sort of diffusive spread of this excitation. And it actually becomes more than just one excitation because of this anisotropy. And this is done here for 21 sites, where basically each part is a strongly coupled spin boson model. Okay, so it's a chain of spin boson. You can also use the fact that you've done all the multi-time correlations correctly in some other way, namely looking at a spin chain, here again an XYZ Heisenberg spin chain, with a hot and a cold bath on each ends, so with hot and cold leads. And you could ask the question, what is the temperature of an intermediate spin at the steady state at late times? And asking such a question is already a little bit weird for a lot of people, because first of all, it's non-equilibrium, and second of all, everything is strongly coupled. So just looking at the state will not be very informative about whether it's thermalized or not, because you would have to be able to diagonalize the entire system. But because we've taken care of correct multi-time correlations, we can use the fluctuation dissipation theorem to check whether it's consistent with being thermalized. So we can simulate this, and then using the method I showed before, and for long times, and then extract two-time correlations and see whether they obey the fluctuation dissipation theorem, and particularly for what temperature they do. So from this, we can infer sort of an effective frequency-dependent temperature. For something that's thermalized, independently of how strongly it's coupled, this should be completely flat. For every frequency, it should be a certain temperature.
Yeah, but that's obviously for a very small bias between T hot and T cold, right? This is linear response theory. So still, out of equilibrium, I agree, but only a small amount away from equilibrium, yeah? Otherwise, there's no way to define temperature, as you said.
Not sure that I understood the comment here.
Yeah,
so this limited is not, so it's not, so the statement about multi-time correlations is not really linear response theory, in the sense that it's an exact statement. So this is exact, it's not an approximation. So calling this the fluctuation dissipation, that is linear response. But the statement about the two-time correlations, it is an exact statement for anything that's thermal, independent of any coupling strength.
I fully agree, but I feel we should be careful, because I mean, if you have a very strong temperature bias between, you're very far away from equilibrium.
Yes.
Yeah. What can you say about those states and the fluctuation dissipation?
Oh yeah, okay. That's maybe the answer here. So here, as I said, so the fluctuation dissipation theorem should tell me, so if I take this, so I compute this, and I just invert this for T. This is what I plot here for each of those spins. Okay? If something is thermalized, then this must be straight. From this, I cannot conclude that it is thermalized, but I can conclude that if it's not flat, then it's certainly not thermalized. Okay, but I can still, in this case, get some sort of physical insight into what is happening, hopefully. So in this case, I actually can see that somehow at a high frequency, it looks like there is actually a good temperature gradient, whereas some mid-frequency, it looks like that the inner spins act as if they were in a common, had a common mid-temperature. Okay, so the statement about using two-time correlations here, strictly speaking, can only say if this is not straight, not flat, then it's not thermalized, right? So it's a necessary condition that it's straight. But the point here is that you can use it because you've correctly computed it, okay? Which would not be the case if you used Lindblad master equations. Anyway.
You do get appropriate thermalization, but only if you use a global picture, not the local type of interaction.
No, even in the global one, you do not get that. So if you have a single spin single environment, and even in a weak coupling limit, it's crazy, yes, and you compute the two-time correlations of that, they will not look thermalized, although it definitely has to thermalize. And this is known since 1996. So Ford and O'Connell, with a paper entitled "There is no quantum regression theorem," they exactly show that the two-time correlations of an Lindblad master
From
equation.
that
even in a
perspective,
weak
maybe
coupling
you'll
limit,
have issues, yeah, but you still get e to the minus beta h. So,
that's in the weak coupling, and that's for the
Yeah.
state. Yes.
well, you would
But in
only
heat-
expect thermal states. We should,
Yeah. Okay.
we should
good.
talk, yeah.
So no,
sorry.
it's fine because I'm at the end of my talk anyways, and we can discuss further afterwards. So let me briefly mention that we have this Python package where we have a lot of the methods mentioned before available, and you can just basically plug and play. So it's really in the spirit of Qtip. So don't need to understand the tensor network stuff behind it. And let me also thank my former supervisor, Jonathan and Brendan, and also my former colleague, Denius, on this work, especially on the time-evolving block decimation things. Also some very insightful discussions with Felix Pollock about process tensor formalism and some other people that I've worked with on related projects. So let me sum this up. So I hope I've convinced you of the interesting relations between the notion of quantum Markovianity, multi-time correlations, and the dynamics of many-body open quantum systems, and that the process tensor is a good formulation to think about those things, and that the process tensor in matrix product operator form, but potentially also in other forms, can be very useful also to do numerical simulations of actual physical systems. So with this, I think I close here.
We have some more time for questions, if there are some. Yes.
So I think that I understand that you are using it as in a more general way, and how you store it or how you compute it is not the crucial point, right? So great, but then I would like to understand why, Jonathan, you said that the kernel in the GQME would not qualify for that because it doesn't do all the things that the process tensor does.
So the kernel and then also the Nakima 20 and those things, they are interested in the evolution of the density matrix. So they are there to give you information about how the state evolves in time. And the question on multi-time correlations is just not described by that.
Why not?
And because of counterexamples I showed, right? So we have something where the evolution. So I had this counterexample with the just before with the stochastic mixture of decay processes. For this, the evolution is completely a Markovian evolution in the sense that you can write down a Lindblad master equation, but you will not know the multi-time correlations from.
But the result is multi-time correlated. The density matrix is, if you compute it correctly.
Yes.
And
yes, and the Lindblad master equation is not correct in that sense.
No, I didn't say Lindblad. I said GQME.
Yes. Okay.
Nakajima, that one. That
Yeah.
is correct. A correct
So
equation
the
if you have the kernel
equation,
correctly.
Okay, so in the Nakajima 20, I would have to understand this.
So we have actually published that already in writing the kernel of the Nakajima-Swansik equation as a tensor train. So it's possible.
Okay.
it doesn't, I will argue, it doesn't matter how you write it, if you compute it correctly, and there, of course, usually it's computed in a very inefficient way, but if you compute it correctly, if you have the correct kernel, then it does have everything in it.
Gerald, could I just ask you for a clarification here? The process tensor is a map, I thought, from the set of operations on the density matrix to a final density matrix. It's not a map, which I would have thought maybe that's the case for the kernel of the Nakajima-Swansea equation, from the history of the density matrix under a particular evolution to a final density matrix.
What's the difference in the two things?
You can look at it from a simple
I think
counting
Gerald's
argument.
example
I think
is
that's
exactly
right.
why they're different, right? But Gerald's example is not of picking a particular of a stochastic mixture of processes, is not something that you can describe in terms of the history of evolutions under a single Hamiltonian. You have to figure out what happens for all those three Hamiltonians and then average them at the end. And that's not.
Okay, I thought we were talking about, sorry, I thought we were talking about dynamics under a particular Hamiltonian here.
No, I'm talking about exactly the thing that I described to you, where it said we have three Hamiltonians here, and we have a stochastic mixture of those.
I see, so, okay.
But I don't think that matters. So formally you can show that if you take process tensors with 3-point correlation functions, then that's enough to construct any Nakajima-Swansea master equation. So said differently, Nakajima-Swansea master equation accounts for only 3-point correlation functions.
Multi
3-point.
Why?
Only 3.
Why?
You can formally show that. So you can think of it as rho dt is difference in 2-time density matrices. So that's 2-point correlation function. And it somehow depends on the initial condition. So that's 3. But you don't ever need 4 or 5 or 6-point correlation functions to reconstruct the Nakajima-Swansea master equation.
Are you saying, okay. Are you saying, sorry,
You have to keep pushing.
yeah,
You want to use
can
this
turn my
one?
hand up.
Yeah.
Yeah.
But I want to say, this sounds like a rather technical discussion at this point. I mean, it sounds important, but I mean, it doesn't seem like something we're gonna settle.
It might be a good
Can I just make like a very quick
So
comment?
let's push this one to a longer discussion or a group discussion. That's okay, because I think we had a question in the back.
Oh, no, I was just gonna make a quick comment.
Okay, well,
with regards
if
to this.
everyone's interested, and we can keep going for another couple of minutes, that's fine.
I mean, it's just a very quick comment. I mean, if you look at a very simple counting argument, what does it take to propagate your initial density matrix using the GQME from time 0 to n time steps? Well, the kernel, if it's acting on a d-dimensional system, at each, if you discretize time, you have a value for the kernel, which is a map acting on like a space of d squared objects to d squared objects. You have n of these if you have n time steps. So then, in order to formally account for this evolution over n time steps, you have a linearly growing number of objects you need to keep. But for the process tensor, you need to keep track of an exponentially growing number of paths. So these are just completely different objects. Like you can derive one from the other, but I don't think you can go backwards to get the process tensor from the Nakajima-Swansea kernel.
I thought the question is, what do you need to get the correct dynamics? Have a map that gives you a correct dynamics.
It sounds like your answer is that the process tensor would give you the correct dynamics, like, and so with the other for certain properties, but the process tensor sort of strictly more general. Like
Right.
Contains the other,
Yeah.
One contains the other.
Right.
It sounds like it's what you're saying,
Yes.
right? Is that?
Is it a given Hamiltonian?
Yeah, I mean, this
For a
is
given
just a
Hamiltonian.
very general statement, I guess, about any kind of time
Yeah,
evolving map.
but
that
if
could
we
be-
talk about, yeah, a given Hamiltonian,
Uh-huh.
then assuming that we don't disagree that on, with the correct calculation, the GQME is correct, right? Then it contains all the information required to propagate the reduced density matrix, and then if you accept that that's the map you're looking for,
I'm not
maybe
just
I'm missing
looking for,
something
no,
there.
I'm not just looking for the map of how to reduce density matrix involves. That's pretty much the point. Because here in this example that I showed here, which I didn't talk through, The evolution, so the density matrix here will not give you any information about what Alice prepared here. So you can look at the density matrix as much as you like, you will not find this information. But you can look at multi-time correlations. So here you see I probed the system at 4 different times, and I can get the entire state back. Okay? So in this case, the information is encoded in the 4-time correlations, and there is no information in the evolution of the density matrix. Okay, so I do not agree if you say that all we're interested in is the evolution of the density matrix. Exactly the point of this. I also am interested in the multi-time correlations, and that is important also because of this, right? Because here we're probing multi-time correlations. Okay.
You're saying the converse for them, saying, I think, I was saying, how you
But I'd be-
propagate everything.
I'd be really interested in a more detailed discussion of this, maybe even with some of the diagrams tomorrow. I think would be good. But I think unfortunately we're out of time now. But thanks for really clear talk.
Thank you.